As we explore the various applications of the concept of statics class, I want you to keep in mind we are using the same process to look at new systems. So we're going to draw Freebody diagrams, do a force and moment balance, solve some geometry, add any force models that need to happen, things like springs or other types of friction, or weight or other physical phenomena, and then finally we solve for the unknowns. So, new applications, no new physics. Today we're going to look at wedges and screws to mechanical devices. A wedge is a machine that can move or adjust a heavy load by transmitting an applied force into a much bigger force, transforming an applied force into a much bigger force. Just like pulleys, it comes at a cost. We might get a huge force, but you have to move it a long distance to get anything to happen. So you're trading distance for force. Here's an example of a load marked with its weight in W, and a wedge marked with an applied load P that would be used to, say, support it. And what we're going to do is we're going to draw two free body diagrams here. The free body diagram of the load, which is, again, experiencing its weight. It's also experiencing a normal force. I'm going to call it N3. I'm drawing this out of order, but that's okay. It's experiencing a friction force that's opposing it sliding down. So that would be, say, mu3 N3. It's going to experience a normal force that acts between it and the wedge. I'm going to call that N2. And it's experiencing a friction force between the wedge and the load here. So we'll call that, say, F2, and maybe make that mu2 times N2. Just to make you see that we could actually find it. Let me slide up here just a minute. Like so. We're also going to draw a free body diagram of the wedge, which looks something like this. The wedge is going to have N2 acting on it as well, equal and opposite. Same with the friction. The friction at the interface force equal and opposite. So F2 again, and that's mu2 N2. We still have the applied load P, and we have the normal force here, say N1. If you wanted to, you can include the weight of the wedge, but maybe that's trivial compared to the weight of the main load, so we don't have to deal with it. Or we could, whatever you like. Call it W2, whatever. And then lastly, we have the friction force along the wall on the floor here. We call that F1. Make that, say, mu1 and 1. What I want you to see here is, again, because we have common forces that are equal and opposite to each other, we get to write a grand total of 6 equations, and we could solve for up to 6 unknowns, which we have. Just to give you an idea of the power of a wedge, imagine if the angle here that this wedge was cut at happened to be 10 degrees. If theta is equal to 10 degrees in this system, then what we discover is that the y component, if we make y vertical and x horizontal, the y component of the normal force N2, the force between them, which is the force pushing up on the load, is equal to 5.76 N2x. In other words, however hard I pushed on it horizontally, I get a almost 6 times multiplier pushing up on it. Now, we lose some of that because of the fact that we have the friction forces, and so P doesn't get to only be 1/5 or 1/6 of the load that we're trying to do. It's going to have to be a little more than that to overcome friction too. But we've saved ourselves a lot of force by using this wedge. Next up, we can look at screws. Screws really do two things. They can either act as fasteners, where they clamp things together, or they can act as power transmission, where they actually cause motion. What I want you to realize is that a screw is nothing more than a wedge that's been coiled around a shaft. And so when we look at screws, it's just a wedge. The geometry is inconvenient, but it is just a wedge with some r's and thetas thrown in there for good measure. If you've never seen something that does power transmission, one version of this would be, say, a linear actuator like this, where there's a motor at the end, it rotates the shaft, and as that shaft rotates, the box in the middle slides up and down according to which direction you turn. So you rotate the shaft and the block moves. This has lots of uses. For example, in a 3D printer, we could use these to move the print head and the part around that you're making. So this 3D printer here has two of these devices in it. One that is at the print head itself. This is going to slide back and forth. And one down here that is going to move the whole table in and out of the page here. And those 2 degrees of freedom give us enough axes that we can position the print head anywhere we like. So that's a use for a screw that you may not have considered.